under thermal physics. Question 1. Define the specific latent heat of fusion of a substance. We have a formula from our data booklets, Q equals to mL, and we can rearrange L equals to Q over M. This specific latent heat of fusion, L, Q over M. Q is a thermal energy per unit mass. So energy released when a unit mass of liquid freezes to become a solid at a constant temperature. So we need to write a constant temperature to get a second mark. Reversals are correct. The energy absorbed when a unit mass of solid melts to become liquid at constant temperature. Definition is definitely specific latent heat of fusion is a thermal energy per unit mass. So energy released when a unit mass of liquid freezes to become a solid at constant temperature. Or energy absorbed when a unit mass of solid melts to become liquid at a constant temperature. So during melting or freezing, the temperature does not change. I explain in terms of molecular model of matter the relative magnitude of specific latent heat of vaporization of water and the specific latent heat of fusion of water. Potential energy changed during a change of state, or bonds weakened or broken during change of state. Potential energy change is larger or greater for vaporization than the fusion, or more energy is required to break the bond than to weaken them. So if you look at vaporization is more into breaking the bonds, while the fusion is to weaken the bonds. So specific latent heat of vaporization is greater than the specific latent heat of fusion. Potential energy change during the change of state. We discussed this in our potential energy change during a change of state, but temperature does not change. Or bonds are weakened or broken during changes of state. So potential energy change is greater for vaporization than fusion, as more energy is required to break the bonds during vaporization than to weaken during fusion. So specific latent heat of vaporization is greater than specific latent heat of fusion. A piece of ice is placed into a beaker of water and melts completely. Following data available: initial mass of ice 20 gram, initial mass of water 250 gram, initial temperature of the ice 0 degrees Celsius, initial temperature of the water 80 degrees Celsius, specific latent heat of fusion of ice 3.3 times 10 to 5 joule per kilogram, specific heat capacity of the water 4,200 joule per kilogram per Kelvin. Determine the final temperature of the water. We have ice and we have a water. So ice at 0 degrees Celsius and a water at 80 degrees Celsius. And we are looking for the final temperature of the water. The first thing, ice need to melt completely, right? So melts, we have Q equals to mLF. So that's where the specific latent heat of fusion is applied. Then temperature from 0 increase to T. We use Q equal to MC delta T. For water, the temperature from 80 drop to T. So we have a Q equals to MC delta T, change in temperature. We have Q gain, the ice gain energy, and Q lost, the hot water lost thermal energy. Ice gain thermal energy. First of all, it should melt first. So melting process, we have M, mass of the ice, LF, specific latent heat of fusion of ice. After melted, we have mass of the ice, specific heat capacity of water, and T minus 0 equals to the water lost, the mass of the water, specific heat capacity of the water, and AT minus T. Let's plug in the values. Mass of the ice 0.02 times 3.3 times 10 to 5 plus 0.02 times 4,200 times T equals to 0.25 kilogram times 4,200 times AT minus T. If we solve this, we get 68 degrees Celsius. State two assumptions that you made in your answer to part FI. So what is the assumption we made here? We assume that no energy is given up to surrounding environment. No energy is absorbed by beaker and no evaporation of water. So we probably made these three assumptions when we write Q gain equals to Q lost. Q lost here does not mean lost to the surrounding. Q lost means the water lost thermal energy, but the lost thermal energy is given to ice. In our assumption is no energy is given to surrounding or environment, no energy absorbed by beaker, and no evaporation of water. Question number 2. As its melting temperature, molten zinc is poured into an iron mold. The molten zinc becomes a solid without changing temperature. Outline why a given mass of molten zinc has a greater internal energy than the same mass of solid zinc at the same temperature. So same temperature means the average kinetic energy of the molecules is the same. And we know interatomic potential energy or potential energy of the molecules is greater for liquid as the distance between particles are far apart. As internal energy is a sum of potential energy and kinetic energy of the molecules. Even though they have the same kinetic energy, but liquid has a higher potential energy, so the internal energy is greater for molten zinc as it is liquid. The zinc is allowed to cool in a mold. The temperature of the iron mold was 20 degrees Celsius before molten zinc. As its melting temperature was poured into it, the final temperature of the iron mold and the solidified zinc is 89 degrees Celsius. The following data available: mass of iron mold 12 kilogram, mass of zinc 1.5 kilogram, specific heat capacity of the iron is 440 joule per kilogram per Kelvin, specific latent heat of fusion of zinc is 113 kilojoule per kilogram. We need to convert that kilojoule into joule, so 113 times 10 to 3 joule per kilogram. Melting temperature of the zinc 420 degrees Celsius. Use the data to determine the specific heat capacity of the zinc. So we have iron, which is mold, and we have a zinc, right? And temperature of the iron is 20 degrees Celsius, and the final temperature of the iron mold and the solidified zinc is 89 degrees Celsius. The melting temperature of the zinc, which is also freezing temperature of the zinc, 420. In this case, melting temperature and freezing temperature is the same. Zinc freeze first, and in temperature from 420 drop to 89, while the iron temperature from 20 increase to 89. As the zinc is freezing, so we have a phase change, so Q equals to MLF, specific latent heat of fusion. Thermal energy equals to mass times the specific latent heat of fusion, and then temperature from 420 drop to 89. So that is Q lost, thermal energy lost. And we use, as we have a change in temperature, we use Q equal to mc delta T. As for iron, temperature increase from 20 to 89, we have Q equals to mc delta T. So we have a Q lost, the thermal energy lost by the zinc, equals to Q gain, thermal energy gained by the iron. Q lost is energy lost by zinc. The first thing is freezing. So we have ML plus temperature from 420 dropped to 89. So we have MC 420 minus 89. So this is the mass of the zinc, 1.5 times the specific latent heat of fusion of zinc, 113,000 joule per kilogram, plus mass of the zinc, 1.5 times specific heat capacity of the zinc times 420 minus 89, which equals to Q gain, that is M iron, C iron, and 89 minus 20. So the mass of the iron is 12 kilogram times the specific heat capacity of the iron is 440 times 89 minus 20. And that equals to 195,000 divided by 1.5 times 420 minus 89 equals to 390 joule per kilogram per Kelvin, or 390 joule per kilogram per degree Celsius. E. Describe with reference to molecular behavior the process of melting ice. In ice, the particles or molecules vibrate about a fixed position. So as their total energy increases during melting, the molecular overcomes the attractive force between them. And in liquid water, the molecules are able to migrate, change position, or slide past one another. F. A container of negligible mass isolated from its surrounding contain 0.150 kilogram of ice at a temperature of minus 18.7 degrees Celsius. An electric heater supplies energy at a rate of 125 watt. I. After a time interval of 45 seconds, all of the ice has reached a temperature of 0 degrees Celsius without any melting. Very important here, we need to read carefully. So after a time interval of 45 seconds, all of the ice has reached a temperature of 0 degrees Celsius. So temperature from minus 18.7 reached 0 degrees Celsius without any melting. So we don't have any specific latent heat of fusion. Calculate the specific heat capacity of the ice. There's no phase change as the temperature from minus 18.7 degrees Celsius reached 0 without any melting. So there's no phase change. So we're going to use Q equal to mc delta T. And energy supplied is from the water heater, right? Electric heater. So electric heater provides energy. And we know power formula. Power equals to electrical energy over time taken. And the electrical energy equals to power times T. That is, power is 125 times time taken is 45. That gives us 5,625 joule. So we assume that no energy lost to the surrounding. All the electrical energy converted into a thermal energy. That means Q equal to mc delta T, and all the electrical energy converted into thermal energy. So Q equals to E. That is C equals to Q over M times delta T. Thermal energy is equals to electrical energy. That is 5,625 divided by mass is 0.125 times temperature, final temperature 0 minus 18.7, so that gives us plus 2.01 times 10 to 3 joule per kilogram, which is approximately 2010 joule per kilogram. The following data are available: specific heat capacity of the water 4200 joule per kilogram per Kelvin, specific latent heat of fusion of ice 3.3 times 10 to 5 joule per kilogram. Determine the final temperature of the water when the heater supplies energy for a further 600 seconds. We can find the energy available from the electric heater, which is energy equals to power times time, and powers remain unchanged, which is 125 times time taken 600, we get 75,000 joule. So this is energy available from the electric heater. So electric heater supplies 75,000 joule of energy, and 75,000 joule of energy is required to melt the ice, which is specific latent heat, and then to raise the temperature to certain degree. So mass of the ice 0.15 times specific latent heat of fusion 3.3 times 10 to 5 plus mass of the ice 0.15 times specific heat capacity 4200 times T minus 0. And if we solve this question, we get T equals to 40.5 degrees Celsius.